most distribution systems, there is not always a grounded conductor on the primary side of the distribution transformer. Even when there is a grounded conductor, it is not typically directly bonded to the secondary grounded conductor of the transformer. The secondary side of the distribution transformer is typically grounded at the service and at the utility transformer secondary. The return paths to a given transformer secondary are typically the electrodes connected to the secondary. These include ground rods, washer pipes, or other conductive objects connected to the grounding electrode system. In some systems, a neutral conductor is used to connect the transformer secondary to the grounded conductor at the service. Equipment grounding conductors are conductors that connect electrical equipment to the grounding electrode system. While there may not be a direct bond between the primary and secondary grounded conductors, there is often some degree of bonding between grounding electrodes in a neighborhood due to, firstly, shared underground infrastructure such as water pipes or gas lines, secondly, buried electrical conduits, and thirdly, lightning rods connected to the grounding electrode system. This bonding provides additional return paths for fault currents and helps to equalize ground potential between different locations. However, it is important to note that the level of bonding between grounding electrodes can vary depending on the specific circumstances and the age of the infrastructure. Therefore, it is not always reliable to assume that all grounds in a neighborhood are effectively bonded together. Let's delve deeper into the specifics of grounding in electrical distribution systems, starting with the primary side of distribution transformers. In many systems, the primary distribution voltage, which could be anything from 4.16 kV to 34.5 kV, may or may not have a dedicated grounded conductor. Several configurations exist. Firstly, there's the delta configuration, where the primary windings of the transformer are connected in a delta formation. In this setup, none of the three primary conductors is intentionally grounded at the source. The system relies on impedance grounding or ungrounded operation, with ground fault detection mechanisms to alert the utility of a fault condition. Secondly, we have the Y configuration. In this case, the primary windings are connected in a Y formation, and the neutral point of the Y can be grounded. This provides a direct path for ground fault currents to return to the source. The decision to ground the primary neutral often depends on factors such as system stability, protection requirements, and coordination with other protective devices. Thirdly, there's the ungrounded system. An ungrounded system doesn't have an intentional path to ground. However, it has a distributed capacitance to ground, and therefore, under a ground fault condition, the voltage on the unfaulted phases rises to line voltage. This can cause stress on insulation. It is also difficult to locate the first fault. The advantage of the ungrounded system is that it can continue to operate with a single ground fault. However, a second ground fault can cause a short circuit. Moving on to the secondary side, the situation is more standardized. The secondary winding, typically providing 120/240 volts for residential service or 208Y/120 volts or 480Y/277 volts for commercial and industrial applications, is almost universally grounded. This grounding is achieved by connecting the neutral point of the secondary winding to a grounding electrode system. This system consists of ground rods, metallic water pipes, or concrete encased electrodes, all bonded together to form a low impedance path to earth. This grounding serves several critical functions. Firstly, it limits the voltage to ground during normal operation, preventing dangerous overvoltages that could pose a shock hazard. Secondly, it provides a low impedance path for fault currents to return to the source, facilitating the rapid operation of overcurrent protective devices such as circuit breakers and fuses. Thirdly, it stabilizes the voltage with respect to ground, minimizing noise and interference in sensitive electronic equipment. As for the return paths to the transformer secondary, there are multiple avenues for current to flow back to the source during both normal operation and fault conditions. Firstly, there are the grounding electrodes connected to the secondary neutral. These electrodes provide a direct path for ground fault currents to return to the transformer. The effectiveness of this path depends on the quality of the grounding electrode system and the soil resistivity. Secondly, there is the neutral conductor. In systems with a grounded neutral, the neutral conductor provides a dedicated return path for unbalanced load currents. This conductor is typically bonded to the grounding electrode system at the service entrance. Thirdly, there are the equipment grounding conductors. These conductors are connected to the metal enclosures of electrical equipment and provide a low impedance path for fault currents to return to the source. They are bonded to the grounding electrode system at the service entrance and at various points throughout the electrical system. Regarding the bonding between grounding electrodes in a neighborhood, there is often a degree of interconnectedness due to shared underground infrastructure. Water pipes, gas lines, and buried electrical conduits can all provide conductive paths between different grounding electrode systems. Additionally, lightning rods connected to the grounding electrode system can further enhance this interconnectedness. This bonding provides several benefits. Firstly, it helps to equalize ground potential between different locations, minimizing the risk of touch potential hazards. Secondly, it provides additional return paths for fault currents, improving the overall performance of the grounding system. Thirdly, it reduces the impedance of the grounding system, lowering the voltage rise during fault conditions. However, it's important to acknowledge the limitations of this interconnectedness. The degree of bonding between grounding electrodes can vary significantly depending on the age and condition of the infrastructure, the soil resistivity, and the presence of insulating joints in underground piping. It's not always safe to assume that all grounds in a neighborhood are effectively bonded together. For example, plastic water pipes are becoming more common. In situations where a fault occurs, current will flow through the path of least resistance back to the source. If the grounding system is properly installed and maintained, this path will be through the grounding conductors and electrodes. This will cause the overcurrent protective device, such as a circuit breaker or fuse, to trip, de-energizing the circuit and preventing a shock hazard. It's important to have a properly installed and maintained grounding system. This includes using the correct size and type of grounding conductors, ensuring that all connections are tight and corrosion-free, and periodically testing the grounding system to verify its effectiveness. Also, ground fault circuit interrupters, or GFCIs, are designed to protect people from electric shock. They work by monitoring the current flowing through the hot and neutral conductors of a circuit. If there is a difference of 5 milliamps or more, the GFCI will trip, de-energizing the circuit in a fraction of a second. These are typically installed in areas where there is a risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Another type of protective device is an arc fault circuit interrupter, or FSIs. These are designed to protect against fires caused by arc faults. Arc faults are dangerous electrical conditions that can occur when damaged or deteriorated wiring creates an unintended electrical discharge. FSIs work by monitoring the electrical waveform for characteristics that indicate an arc fault. If an arc fault is detected, the FSI will trip, de-energizing the circuit and preventing a fire. These are typically installed in bedrooms and other areas where people sleep. The electrical codes provide detailed requirements for grounding and bonding. These codes are based on established safety principles and are designed to minimize the risk of electric shock and fire. It's important to consult the applicable electrical code for specific requirements in a given location. One such example is the National Electrical Code, NEC, in the United States, that provides comprehensive guidelines for electrical installations, including grounding and bonding requirements. It is crucial to adhere to these codes to ensure the safety of electrical systems. Regular inspections and testing of grounding systems are essential to ensure their continued effectiveness. Grounding electrode resistance testing can verify the integrity of the grounding electrode system and identify potential problems. Visual inspections can detect loose connections, corrosion, or other damage to grounding conductors and electrodes. Understanding the grounding principles, return paths, and bonding practices is essential for electrical safety and proper system operation. By following the applicable codes and standards and performing regular inspections and testing, electrical professionals can ensure the safety and reliability of electrical systems. Now let's move on to discussing some common misconceptions about grounding. One common misconception is that grounding is only necessary for safety. While grounding is certainly critical for safety, it also plays an important role in the proper operation of electrical equipment. Grounding helps to stabilize voltage, reduce noise, and prevent equipment damage. Another misconception is that a single ground rod is sufficient for grounding. In many cases, a single ground rod is not sufficient to provide an adequate grounding path. The NEC typically requires the use of multiple ground rods or other grounding electrodes to achieve a sufficiently low ground resistance. Also, another misconception is that grounding is the same as bonding. Grounding and bonding are related but distinct concepts. Grounding refers to connecting electrical equipment to the earth, while bonding refers to connecting different metallic parts of an electrical system together to create a low impedance path for fault currents. Let's discuss some additional details about grounding electrode systems. The grounding electrode system should be designed to provide a low impedance path to ground. This can be achieved by using multiple ground rods, a ground ring, or a concrete encased electrode. The size of the grounding conductors should be based on the size of the service entrance conductors. The grounding conductors should be installed in a manner that protects them from physical damage. The grounding electrode system should be tested periodically to verify its effectiveness. We should also discuss the importance of proper bonding. Bonding is the process of connecting different metallic parts of an electrical system together to create a low impedance path for fault currents. Proper bonding is essential for safety and the proper operation of electrical equipment. The bonding conductors should be sized according to the applicable electrical code. The bonding conductors should be installed in a manner that protects them from physical damage. The bonding connection should be tight and corrosion-free. Now let's talk about the different types of grounding systems. Firstly, there's the solid grounded system. In this system, the neutral point of the transformer or generator is directly connected to ground. This provides a low impedance path for ground fault currents. Secondly, there's the impedance grounded system. In this system, an impedance, such as a resistor or reactor, is inserted between the neutral point and ground. This limits the ground fault current, reducing the risk of damage to equipment. Thirdly, there's the ungrounded system. In this system, there is no intentional connection between the neutral point and ground. This type of system can continue to operate with a single ground fault, but it is important to locate and correct the fault as soon as possible. Now let's also discuss the role of the utility company. The utility company is responsible for providing a safe and reliable supply of electricity. This includes maintaining the grounding system on the primary side of the distribution transformer. The utility company also works to coordinate with customers to ensure that their grounding systems are compatible with the utilities system. Remember that electrical safety is a critical aspect of electrical work. Grounding and bonding are essential for protecting people and equipment from electrical hazards. By understanding the principles of grounding and bonding, we can help to ensure a safe and reliable electrical system. We should always consult with a qualified electrician when working on electrical systems. They have the knowledge and experience to ensure that the work is performed safely and according to the applicable electrical code. Let's also explore the concept of ground potential rise. Ground potential rise occurs where a large fault current flows through the grounding system. The voltage potential of the ground near the fault can rise significantly, posing a shock hazard to anyone who comes into contact with the ground. It is more pronounced when soil resistivity is high, as higher resistance leads to greater voltage drop across the soil. To mitigate ground potential rise, several measures can be taken, including using multiple ground rods, installing a ground grid, and bonding all metallic objects in the area. Now let's discuss surge protection. Surge protective devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning strikes or other events. SPD work by diverting the surge current to ground, protecting the connected equipment from damage. SPD should be installed at the service entrance and at sensitive electronic equipment. We should also discuss harmonics. Harmonics are distortions in the voltage and current waveforms that can cause problems in electrical systems. Harmonics can be caused by nonlinear loads such as electronic equipment and variable frequency drives. Harmonics can cause overheating of equipment, increased energy losses, and interference with communication systems. To mitigate harmonics, several measures can be taken, including using harmonic filters, installing line reactors, and using properly designed transformers. Let's further discuss the impact of soil resistivity. Soil resistivity is a measure of the resistance of the soil to the flow of electrical current. High soil resistivity can make it difficult to achieve a low impedance grounding system. Factors that affect soil resistivity include moisture content, temperature, and the presence of salts or other minerals. To reduce soil resistivity, several measures can be taken, including adding water to the soil, using ground enhancement materials, and installing a ground ring. Now let's delve into the topic of isolated ground systems. An isolated ground system is a type of grounding system that is used to reduce noise and interference in sensitive electronic equipment. In an isolated ground system, the grounding conductor for the equipment is isolated from the building's main grounding system. This prevents noise currents from flowing through the grounding conductor and interfering with the equipment. Isolated ground systems should be installed according to the applicable electrical code. We should also discuss the topic of equipotential bonding. Equipotential bonding is the process of connecting all metallic objects in an area together to create a common electrical potential. This helps to prevent shock hazards by ensuring that there are no voltage differences between different metallic objects. Equipotential bonding is required in areas such as swimming pools, spas, and bathrooms. Now let's discuss grounding in different types of buildings. Firstly, residential buildings. In residential buildings, the grounding system typically consists of a ground rod, a metallic water pipe, and a grounding electrode conductor that connects these electrodes to the service entrance. Secondly, we have commercial buildings. In commercial buildings, the grounding system is typically more complex than in residential buildings. It may include multiple ground rods, a ground ring, and a concrete encased electrode. Thirdly, we have industrial buildings. In industrial buildings, the grounding system is typically the most complex. It may include all of the features of a commercial building grounding system, as well as additional features such as a ground grid and surge protection devices. We should also consider grounding in hazardous locations. Hazardous locations are areas where there is a risk of explosion or fire due to the presence of flammable gases, vapors, or dusts. Grounding in hazardous locations is particularly important to prevent the accumulation of static electricity, which could ignite the flammable materials. Special grounding requirements apply in hazardous locations, as specified in the applicable electrical code. It is essential that all electrical work in hazardous locations is performed by qualified personnel who are familiar with these requirements. Now let's talk about the future of grounding. The future of grounding is likely to be influenced by several factors, including the increasing use of electronic equipment, the growing popularity of renewable energy sources, and the development of new grounding technologies. As electronic equipment becomes more prevalent, the need for effective grounding to reduce noise and interference will become even more important. The increasing use of renewable energy sources, such as solar and wind power, will also require new approaches to grounding to ensure the safety and reliability of these systems. New grounding technologies, such as solid-state grounding devices, are being developed that offer improved performance and reliability. It is likely that these technologies will play an increasingly important role in the future of grounding. Finally, it's worth reiterating that the information provided is for general educational purposes and does not constitute professional electrical advice. Always consult with a qualified and licensed electrician for any electrical work or specific grounding system design. They can assess the specific conditions of your location, consider the applicable electrical codes, and ensure that your electrical system is safe and compliant.